All right, so we'll talk about C programs now. For my information, how many of you have done C? Oh, okay. So pretty much everybody. Excellent. All right, well, in Power PMAC, you can use C for a lot of stuff. Actually, you can use C for virtually every function we've described before, except motion programs. There's no way to write a motion program in C, but you can write PLCs in C, you can do setup in C, you can do all kinds of stuff through C. So it's nice. You might ask, why would I use C ever? Basically, whatever you need to be really, really, really fast should be written in C, because it's like 10 times faster than in script, because script is actually interpreted language. So C is compiled, and for example, if you have a kinematics routine that's really complicated or has iterative convergence or something like that, then you definitely want to write that in C to save your PMAC some resources. Otherwise, it'll take a lot of CPU time to do the convergence. So we have a lot of different C programs available in Power PMAC, and they're listed up here in order of descending execution frequency. So the highest priority C program is the capture compare interrupt. So this runs when you have a capture or compare event in Power PMAC. Capture or compare event occurs when you are looking for a trigger or when you set up position compare like Alex just taught you guys. So this is very high priority, can actually interrupt all of the other categories of programs and can interrupt even phase and servo. So you want to keep that function extremely short in order not to inhibit the phase and servo tasks. Excuse me. The next type of C program is user-written phase, and this runs at the phase rate. So this is useful if you want to write your own commutation algorithm or something of that nature, or current loop algorithm. But you can also use it for non-commutation tasks if you just want a C program that runs at the phase rate. So it's handy for that. Next is the user-written servo that runs at the servo interrupt period. And you can use this for making your own control algorithms. If you know what you're doing, you can program it in there and replace the conventional PID loop that we use for the standard servos. You can also use it for general purpose tasks if you want. It's useful if you just want a program to run at servo rate. Next is the real-time interrupt PLC. RTIC PLC is an acronym that you'll hear. This is the equivalent of your Turbo PMAX PLC C0, which was a compiled PLC that would run at real-time interrupt. And this is for general purpose use. You use it for the same purposes as a PLC in script, but it just runs a lot faster. And you can enable it and disable it with useralgo.rticplc equals 1 and 0 respectively. Then we have background CPLCs, also called BGC PLCs, and we have 32 of them, numbered 0 to 31. And all 32 of these will execute every background cycle. So they actually run more often than the background script PLCs. Background script PLC would only run, you'd only run one background script PLC per background cycle, but all of the BGC PLCs run. And lastly, we have general purpose operating system programs, also known as background C programs. And these are run as standalone programs in the Linux environment. They're not scheduled by PMAC. They don't run at any particular determinism. The Linux general purpose OS will allocate the CPU time for that. And you can use this for a lot of different purposes. Some examples we've used it for in the past are getting data from a camera, communicating over Ethernet. We also use it for host communication and data logging and kinematics. Or sorry, not kinematics. You wouldn't do kinematics there, but you could do a lot of different things with a background C program. Oh, and the background CPLCs are enabled and disabled using useralgo.bgcplc bracket PLC number and equals 1. Note that background CPLCs need to be numbered, not named. There's no way to name your background CPLC, so you need to keep track of that. Now let me just show you where all the C programs live in the IDE. Go up to the top of your Solution Explorer, and you'll see the C language folder. And in there we have folders for all the different kinds of C applications available. Background programs is the first one. So you can add new background programs by right-clicking that folder, and then add a new background C application. The background CPLCs are in the CPLCs folder. One of them is in there already, BGCPLC 0. And to add a new background script PLC, or CPLC, excuse me, you right-click CPLCs and click Add a New User CPLC Project. And then you can pick the number, so I picked BGCPLC 1, and it actually creates a folder for that PLC and makes a file with the template for the PLC. Next is the RTI CPLC folder, which has a template for the RTI CPLC for you. We also have an includes folder where you can put header files that you include in various programs, and a libraries folder where you can also add your own C and H files. So C is a source file, and .h is a header file. And then lastly, we have the real-time routines folder with usercode.c and usercode.h. And in there we have a template for user-written phase and user-written servo functions. I want to note that you see this cancel icon next to the file name. That means that the build action is set not to compile by default. So if you want to actually compile this, you go to Properties by right-clicking the file, go Properties, and then you would change the build action from Content to Compile, and then PMAC will actually build that program. So the way you build C programs is by right-clicking your project name, and you can click Build. And that does not necessarily download the program. If you want to build and download, you can click Build and Download all programs, and it'll build your C and then download it for you. So let's move on. The capture, compare, interrupt function is triggered on a capture or compare event on any channel of a PMAC 3 style IC. So PMAC 3 style IC is accessory 24E3 or any other gate 3 product you might find in the brick series, for example. Those have gate 3s in them. And this can execute really fast, upwards of 60 kilohertz. And you write the function inside usercode.c, and you have to define it, or declare it rather, as a particular name. It's of type void. The name is capcomp ISR, and it receives a void. And then you enable the feature with useralgo.capcompinter equals 1. So you were asking me in the back there about basically logging captured positions. This is the program that you would use to do that. I'll show you an example of doing that exact thing. This is a block diagram explaining the functionality of the interrupt. Shows you basically how the data is flowing around the captured positions and the triggered captured point and all that. It's kind of a confusing diagram, but it's there for your reference. So the capture and compare interrupt is controlled by the structure gate3 sub I.int control. This is a 3-part structure. So the lowest byte is the interrupt status. It tells you which interrupt actually occurred. The middle byte is the interrupt source. This also tells you which signals triggered the interrupt. And the high byte is the interrupt enable byte. And this allows you to control which of the possible 4 capture events and 4 compare events for your IC can cause the capture compare interrupt to run. So each bit within each byte pertains to either a capture flag or a compare flag. So bit 0 will pertain to the first channel's compare flag, bit 1 pertains to the second channel's compare flag, and so forth. Then bit 4 represents the first channel internal compare flag. Or sorry, the first 4 bits are the capture flags, and the next 4 bits are the internal compare flags for the channels in your IC. So you set that up before you use the capture compare interrupt. Make sure you set up the interrupt enable byte, and then inside the capture compare interrupt, we actually read that structure to see what caused the interrupt and take actions appropriately. So this is an example doing what you were asking about. Basically, we define your capture compare interrupt with void capcomp ISR void, and then inside here, we're making a pointer to the gate3 IC. And we make some more pointers. One is cap counter and one is cap pause store. So cap counter will log the number of triggers that we experience, and cap pause store is a pointer we will use to index the user buffer and then log the captured positions in the array. And then here we're using function getGate3memptr to assign the memory address to the pointer. We initialize the capture counter to be sys.idata 65535. And then we initialize the pointer that will store the positions in 65536. And then we're adding star capped counter so that basically whenever you capture a position, we will increment capped counter. And then the next time this runs, your captured position will be stored in the next array element of the user buffer up. So you'll keep indexing through the user buffer. And this is how you read the stored position. It's in gate3 chan sub j.homecapped. And something to note, in case you don't remember it from earlier in the training, in order to rearm the capture, you need to read home capped so that you basically tell the gate it's okay to get another trigger. So you read home capped, store that somewhere, and then you can get another trigger. Then at the very end, we write a 1 to int control to permit the interrupt to happen again. So it won't interrupt again until you clear the interrupt status bit, which is in the lowest byte of int control. So does that make sense? Do you have any questions on that? Okay. He asked me about it earlier, so that's why I'm singling him out. All right, so user-written phase will execute after you've associated. Let me start over. Every phase update period, a motor that has motor x.phase control greater than 0 will execute its phase algorithm, whether it's its own default phase algorithm or the one you provide. And then you can associate your own user-written phase algorithm with that motor, and it'll run instead of the built-in one. You can name your user-written phase however you like, but it must accept a motor data pointer. And this is a pointer that allows you to get access to all of the structural elements for the particular motor that's executing this algorithm. And you can access actually all the memory in PMAC, so you can use this for general purpose as well. And you can even use floating point math inside the user-written phase. Something I forgot to mention is that in the capture compare interrupt subroutine, you cannot use floating point math. It's integer only. That's why we have to use the user buffer, because that's the only true integer format that you have access to for basically transferring information between the capture compare interrupt and anywhere else in PMAC. So the form for defining your user-written phase is void, and then the name that you can give it whatever name, and then it receives struct motor data star in PTR. And then at the end of your routine, you can write the phase A and phase B commands, which are basically current commands for phases A and B of your commutated motor. You write that to inptr points to PDAC 0 and 1, respectively, for A and B. And just to give you a little refresher on C, this is called the structure dereference operator, dash greater than. So here, the name of the structure pointer is inptr, and this is a member of that structure that we're pointing to. Then to associate your user-written phase with the motor, you can right-click the real-time routines folder and click on add user servo setup. And then you pick your user phase. Mine's just called user phase, and you pick the motor you want to associate. And then hit apply. What motor was I just on? Yeah. Then you hit apply, and it'll ask you to build and download again. And once you build and download that, it'll start executing if your phase control is greater than 0. So it's kind of nice. You don't even have to have the motor enabled. It can be a virtual motor. It can just be a spare one of these motors, like I associate it with motor 0. And then as long as you've set phase control greater than 0, even if servo control is equal to 0, the routine will run. So it needs to be somehow associated with a motor first, though. And then in your, so you write all that into usercode.c, and then in usercode.h, you need to write your function prototype. Function prototype is just the function declaration with a semicolon after it, and then use export underscore symbol and pass it the name of the function. This makes the function available to the IDE for assignment to a motor. This is an example of using user-written phase algorithm to do sinusoidal commutation. I won't really get into it because it's pretty long, but basically it just takes the phase encoder's position and then looks up the voltage it should command to each phase from a sine table, and then commands the appropriate amount of current to phase A and phase B and PDAC 0 and PDAC 1, like I described before. So user-written servo will run for every motor that has servo control greater than 0 and has been associated with user-written servo. So this algorithm must return a double type, which represents servo command output, and must be scaled within the range of plus or minus 32768.0. And then PMAC will use the result of that algorithm for the servo loop. This also accepts a motor data pointer, and you have access to all of the necessary quantities for writing a servo algorithm, such as commanded position, actual position, falling error, desired velocity, and that sort of thing. You can get at those structure elements from your motor using the motor data pointer. And something to note is that if you want to, you can actually manipulate this motor's motorx.servo dot list of gains, and then you can use the tuning tool to adjust your own gains. So if you're going to use a KP in your user-written servo, you can, instead of creating a local C variable called myKP, you can just use PMAC's motorx.servo.kp, and then you can tune it using the software, which is handy. If you don't do that, then the software doesn't know what gains are used. So this is what the declaration looks like. It returns a double. You can name the algorithm whatever you want, and it receives struct motor data star MPTR, just like before. You use the same user servo setup to configure which motors will use your user servo that we used for user phase. And then the IDE will manipulate motorx.control and set it equal to useralgo.servocontrol address subi for you. So this is a address in memory representing the start of your servo algorithm function. Other threads. We'll talk about that more later. And this is what the code template looks like. So by the way, I just want to point out a couple things about the code template that's handy. gplib.h is where the vast majority of the PMAC related stuff is. So to get at anything PMAC, you need to have gplib.h included. And ppproj.h actually contains all of the numerical indices that your named variables have been translated to. So for example, your first global is actually 8192 in PMAC, depending on how you've set up the base number, or in C, depending on how you've set up the base number. And I think Alex showed you guys how to set up the base number for globals and so forth. All right, so background CPLCs. Is this your water or mine, Alex? Okay. Background CPLCs will all run every background cycle, and you can turn each one on and off with useralgo.bgcplc bracket PLC number equals 1 or 0, respectively. We have 32 of them, numbered 0 to 31, and each one is in its own bgcplc.c file. And you have to declare each routine as void user underscore PLCC. So you distinguish the different PLCs not by the function name, but by the file name and the folder wherein it exists. That's why when you add a new project, new CPLC project, it'll create a new folder for you because it has to. Excuse me. And again, you don't need to put these in an indefinite while loop because PMAC has scheduled it to run every background cycle. I showed you how to add a user CPLC project. You just right-click on the CPLC's folder and click on Add a New Project. This is the template. And lastly, the background C programs are allocated by the Linux General Purpose OS, and you can actually find the executable file if you navigate through the Linux environment, and you can run it from the Linux terminal and everything if you want. So basically it's just the same idea as if you wrote a program from the Linux terminal using VI or whatever the text editors are in Linux. I forget, VI and Nano or something. And then wrote GCC and typed your program name. So But if you do want to get at PMAC memory, you can just include gplib.h. Now let's talk about some good practices when programming in C. The thing about C is it's very powerful and flexible, fast, but you can really screw yourself up if you don't know what you're doing. So here's some safe practices you can follow. I already explained one. If you have a loop of any kind, especially a while loop, you want to have some sleeps to release control to other threads. And you probably also want to have a timeout to break the loop in case it's gone on too long. So in C, on a Linux computer like PMAC, you can use NanoSleep to yield control to other threads temporarily. NanoSleep receives two arguments. The first one is a structure of type struct timespec, and you have to actually pass it the address of the structure. That's why we precede the name of the structure with an ampersand. In C, preceding a variable with an ampersand means give me the address of this variable, not the value. And then the second argument, I forget what it means, but you generally always set it equal to null. And it will yield the amount of time you specified inside the timer variable in nanoseconds. And it's pretty reliable. Doesn't have much jitter really. NanoSleep's also the safest yield. It won't interrupt threads scheduling and anything like that. I think there are some thread unsafe yield functions in Linux, like microsleep or something. I can't remember. usleep. But anyway, the way that you construct the timespec structure is like this. It has a seconds part, TV underscore sec, and then a nanoseconds part, TV underscore insec. So I made a cute little function that basically just takes the amount of time you want to sleep in seconds, breaks it up into whole part and nanosecond part for you, and then returns your timer, and then you just dump that into your NanoSleep. You can also take my function here, my sleepsec. It'll actually just do all that for you. So you can use my sleepsec just like call timer in a script PLC. So that's why I'm spending a lot of time on this, because you'll actually use it quite a bit. This is the best way to create a delay in your C program. So you can copy this code if you end up writing a C program. My sleepsec is just called like this, my sleepsec, and then you pass like 1.0 for 1 second, for example. And it is in units of seconds. Make sure you pass a decimal value, though. So even if it's just 1 second, write 1.0. Because it does expect to receive a double. So here's an example of creating a timeout. You define your timeout condition. You can put it in a variable or use a pound define. So I do pound define timeout 10.0, represents seconds. And then we want to track the starting time before we begin the while loop. You can get the time in C from get CPU clock. It's in units of microseconds. And then in our while loop here, we want to check if our current time in get CPU clock minus start time has exceeded the timeout. If it has, we break the loop with the break command. And then if it hasn't exceeded the timeout, you can just release the thread for a small period so that you don't watchdog PMAC. All right, so if you're using dynamic memory allocation with the malloc command, you should always use the free command to free up that memory. Otherwise, you can cause memory leakage. It's bad. Something to note is that malloc is one of those thread unsafe functions, so you should never use it in a thread scheduled task, including any of the C programs I just described, other than the background C program. So in user phase, user servo, you should never use this function. And actually, there's a whole bunch of functions like that. You can just Google thread unsafe functions, Linux, and Google will show you all kinds of stuff. Something else to note is that C is not smart about catching when you go beyond the limitation of an array. So if you make an array of 4 elements and try to go to the 5th element, it'll actually crash the program and give you a segmentation fault. So if you're running a program, like a background C program, PMAC will not get that message, and you'll have no idea that the program stopped, which is especially bad if it's like a safety critical program. So be really careful about that. You will, however, see the segmentation fault if you're running the program from the Linux terminal. It'll just print to the standard out that you got a segmentation fault. If at any time this doesn't make sense, let me know, because I'm speaking as though you guys are familiar with C, since everybody raised your hand. Normally I gloss over this stuff really fast, but since you guys know C, then... you should also not use calls to blocking functions in real-time routines. Certain communication functions will block until they get a response. Blocking means that won't release the thread. Like serial communication functions do that, for example. And some TCP/IP communication functions will block unless you've told them not to, so let's be careful there. All right, so any questions on safety when programming C? Something else I want to note, it's not in the slides necessarily, but a lot of people have contacted tech support saying that they, for whatever reason, basically just watchdog on PowerUp, and the first thing I ask is, do you have a C program? And what will happen a lot of the time is they'll start a C program right as PMAC turns on, like they have it in the startup, ppstartup.txt that I was showing you yesterday. And then it does all this computationally intensive stuff before PMAC has even really booted, and you can cause a lot of problems that way. So if you have a C program, call it from a startup background script PLC with some delay after PowerUp, like 3 seconds or something like that, and then you won't encounter that issue.